And we're going to try this recording again. So if there was a glitch before, please forgive me. Welcome to chapter 10. We're looking at Venus and Mars. And quite frequently when we see pictures of Venus and Mars, we see things sort of like what's happening on the screen behind me here. You're shown the pictures of the various planets as being roughly the same size as each other. But the truth is they're not. And I'm going to show you a different picture here. I'm sitting in front of the Earth right now, so it's here. Notice that Venus, over here, over here, yes, this is Venus. Notice Venus is about the same size as the Earth. Notice that Mars, over here, is much smaller than the Earth. It's actually larger than the Moon, but it is smaller than the Earth, and as a result, also smaller than Venus. So when we look at Venus and Mars, one of the things to keep in mind of the two of them is that Venus is about the same size as the Earth and therefore is much more our twin. When we're looking at it geologically, if we slice it open, it looks very similar. If we're looking at the surfaces of them, however, that's when Mars takes precedence, and that's where we get the idea that Mars might be our twin planet along the way. So without any further ado, let me see if I can share my screen here so that we can get on to looking at, nope, I don't want to cancel that there. We'll look at Earth-like planets, Venus and Mars here. So will it give me the slideshow? Play from start. Yes, it will. Okay. So I feel like I'm being all washed out from the light of our computer here, but we'll do the best we can along the way. We have various probes that have gone to both of these planets. We have active probes right now on Mars. The Curiosity rover is still in operation, and it's perhaps the most famous of the ones that are operating. Spirit and Opportunity are two rovers that were a pair, and Spirit stopped operating about 2010. Opportunity stopped just a couple of years ago. And the remarkable thing about both of these is that when they were sent up, they were only rated to last about 90 to 180 days. Spirit lasted about 7 years, and Opportunity about twice that long. So we really do have a lot of oomph from our probes when they work. When they don't work, they often crash and burn. So if you're thinking about signing up to go to Mars, do remember that about 1 in 4 missions that we've sent to Mars have ended by not making it there. So beware, be careful. But if they ever take 50-something-year-old astronauts, I will sign up for that. Of course, by the time we're going there, it'll probably be closer to needing to be a 60-year-old astronaut. But hey, I'm ready to go. So hopefully in your lifetime, hopefully in my lifetime, we will see people walking on the surface. But for now, as you can see here from the picture, Mars is the only planet in our solar system entirely inhabited by robots. So, as I mentioned before, if we slice open the planets, we can see Earth here and Venus here look very similar. They have a similar core, they have a similar mantle, they have a similar lithosphere, which is the part on the surface that's solidified. Notice over here with Mars, it's considerably smaller. Notice everything seems to be roughly in proportion. We have a core, we have a mantle, we have a crust that are all about the same proportions as we have for Venus and Earth. But notice the lithosphere. The part that has solidified has gone much deeper into the planet. That has significant repercussions for the planet because as the lithosphere cools off, as it solidifies, earthquakes, volcanoes, other kinds of tectonic forces shut off. And when that shuts off, it also has atmospheric interference. It has atmospheric consequences. So as we look over here, Mercury and the Moon, notice how much smaller the Moon is than Mars, certainly than Venus. Inside there, we have a huge core for Mercury. It's almost all core. And the Moon is also pretty much solidified. The larger you are, the longer it takes to cool off. The smaller you are, Mars, Mercury, the Moon, the faster you cool off. And the Moon and Mercury have essentially almost completely cooled off. We're going to say over 90%, maybe even 95%. Mars is getting there too. And that makes a big difference between what used to be on the surface of Mars and what's there right now. But let's take a look at Venus first. Venus is in the sky right now in terms of our evening star. If you look up towards the west for about a couple of hours after sunset, and today it looks like it's rather cloudy, but hopefully it won't be here very soon. Here in April and May of 2020, if you look towards the sunset on the evening sky, you're going to see a very, very, very bright light. It's sometimes called the evening star when it happens there. It's not a star though, it's Venus, and it's actually the third brightest thing in our sky. The sun and the moon are the only two things that are brighter than it is. But it won't be there for a long time because it orbits the sun, and as it gets closer to the sun, it will begin sinking lower and lower towards the sunset. The sun will get in the way, and then when it extends out its orbit the other way, it'll start showing up in the morning sky, and then it's called the morning star. Once again, it's not a star. But Venus has an active geological process going on, but we never see it from overhead. Weather reports on Venus are very easy. 100% chance of clouds 100% of the time. We have sent orbiters and landers to Venus. Now, as I mentioned before, we have landers on Mars, and they're rated to last 90 days to 180 days, and they last for a decade and a half, and they're just terrific. When we land on Venus, if it lasts for 2 hours, not 2 years, not 2 days, but 2 hours, we're thrilled. And a large part of that is because of what you're seeing right here. It has such thick, dense atmospheric clouds and pressure that it destroys whatever tries to land on the surface. And we have to structurally reinforce them so that they can last even that brief amount of time. But we never actually see the surface directly in Roy G. Biv light. We can explore it through radar. And we've had quite a number of probes that have gone to Venus over the past half century, and they have taken radar mappings, and we have a pretty good view of what's happening on the surface as a result of that. We can tell, see this brown stuff that's here. That's higher elevations. This blue stuff, if there were oceans on Venus, this is where they would be. This is the lower elevations. And then we have the mid-ranges here. There are no oceans on Venus. It's way, way, way too hot. We're talking 800 degrees Fahrenheit or hotter, 470 degrees Celsius, and that's day and night. So it would all boil away. It would all be gone. But we still have processes that tell us that maybe once upon a time there were oceans on Venus. It's still up in the air as to whether or not that was likely. There is a debate going on right now in the scientific community over that. But if it was oceanic at one point, it's been gone for billions of years along the way. But we can see, just like here on Earth, we have high elevations, mountain ranges, we have tall areas in continents, we have low areas in oceans. That same stuff is true for Venus. And notice we have this large continent that we're seeing right here. That's called Aphrodite. And if you know your Greek and Roman history, especially mythological history, you'll get the connection between Aphrodite and Venus. We do have volcanic activity on Venus, including shield volcanoes. Remember, that's the kind of volcano where stuff bubbles up and builds kinds of islands. And then we have stratovolcanoes. Those are the big mountains that just sort of shoot the lava straight up into the stratosphere. So stratovolcanoes are kind of like Mount Vesuvius that buried Pompeii. Shield volcanoes are like the kinds that build the Hawaiian Islands. We have impact craters on Venus. We can see quite a number of areas where there's been an impact, and we see a bit of a central peak. This one here in the upper right corner actually looks like it is a little face in there. And we have this area of stuff that's ejected out as there was a big impact, and that's called an ejecta blanket along the way. So here we have different areas that have been hit. Here we have a cluster of crater impact sites. This might have been something that as it was coming in actually broke apart in the atmosphere and hit in a couple of different areas along the way. This stuff here was caused by something that was probably about maybe half the size of Ellettsville. So it was a pretty big one that hit there. These are more shield volcanoes. These are sort of called pancake volcanoes. And what happens is the stuff sort of bubbles up from the center and just sort of builds a big dome. We don't have any kind of water erosion taking place on them, but notice we do have some cracks that are happening there. So we do have tectonic forces that are breaking things apart. And these can be as much as about a mile high. So they can actually be pretty tall along the way. Our tallest mountains on Earth would be about 5 times taller than this. So we're not sort of talking huge structures, but that's not a surprise because again, notice the size of Venus and the Earth over here. Let's see if I can point to the right ones. The bigger your planet, the smaller your volcanoes and the smaller your mountain ranges are going to be because gravity is going to pull them down. So you actually get bigger you get bigger volcanoes, bigger mountains over here on Mars than you do over here on Venus along the way. Here is another crater. Has fewer craters than the Moon, Mercury, or Mars, and that's because even though it doesn't have any water erosion, it has a very thick and active atmosphere. The Moon and Mercury have no atmosphere and no water in terms of sort of glacial or oceanic or even river kinds of water. So nothing's wearing them away. So they've preserved their craters a lot more. And Mars has not had an ocean and has a very thin atmosphere, so it's not wearing things away nearly as much. So we have craters on Venus, but they get worn away fairly quickly. And here is an area that is called Miss Piggy. You may have heard of the face on Mars, and we'll get back there later. There's a face on Venus too, and you can sort of see we have the eyes and the snout, and we have these sort of little pinhole kinds of things here. We have a pancake volcano up here in the middle. So we have, this is actually called Fotla, which is a Celtic name. Not everything is named after Greek and Roman things anymore along the way, but we do have some impact sites, and we do have some volcanic activity that's here. And we see these fractures that have happened along the way, from most likely from an impact that's happened there. But we do have tectonic forces that are pushing things together or pulling things apart. And here we can sort of see this crevice that is opening up as plates pull apart. Now, here on Earth, as we talked about in previous lectures, we have a lot of plates that are moving. We have the North American plate, South American plate, and the Eurasian plate and other things. We got really big plates here. On Venus, we have a lot of platelets. So instead of having things the size of countries or the size of continents, we have a lot of smaller plates that are maybe the size of a small state or even counties that are sort of moving along. And we can see all of these different kinds of stress fractures here. This area here is probably about 35 to 40 miles across in the bottom here. And it's probably about 25 miles high. So this is about the size of a big American county. And notice how many fractures and cracks and ridges we have in there. We have actually landed on Venus. This is one of the probes that's landed there. You can see it looks like it's already corroding because as things land, the atmosphere on Venus is 95 times thicker than the atmosphere here on Earth, which means here on Earth we have a barometric pressure. Stuff is pushing down on us at about 15 pounds per square inch. You multiply that by 95, you have tons of stuff. If your body was on Venus, you would have several tons pushing down on you. If you're lying flat, you could never raise yourself up. Not that you'd need to, because there's also a layer of sulfuric acid in the atmosphere. So as a probe goes through, it gets coated with this stuff and it begins to eat stuff away. So not only do you have to worry about things being crushed, you have to worry about things corroding very, very quickly. And that's why, as I said before, right now the record for anything lasting on the surface of Venus is actually right about 2 hours. Most things last between 15 minutes and 30 minutes. Here's another image from a spacecraft, a Venera spacecraft. The Venera spacecraft were operated by the Soviet Union and by Russia. Almost through informal agreement in the early space age, Russia concentrated more of their research on Venus, and NASA and the United States concentrated more of their research on Mars. And they shared information back and forth on a scientific basis. There was no military strategic advantage to either place at that time. So we didn't sort of duplicate efforts. We actually shared material, and especially in the scientific community. So the Russian exploration of Venus through the Venera probes is actually our primary way of knowing what's happened there along the way. We can see these rocks. They look like once upon a time they were underwater. And that's one of the things that has made people try to reconsider whether or not there might have been some oceanic or at least lake kinds of formations on the surface of Venus once upon a time. The atmosphere of Venus is heavy, heavy CO2, carbon dioxide. That is a greenhouse gas. That's why it is so hot on Venus. And if you have 95 times the atmosphere and a lot of it is a greenhouse gas, you're going to trap a lot of heat there. So that's why it is 470 degrees Celsius, over 800 degrees Fahrenheit, hot enough to melt lead on the surface. Another reason why probes don't last. But notice here we have these sulfur clouds, the sulfuric acid. And we do have, as any atmosphere would have, as we get higher from the surface, it gets lighter, it gets cooler along the way, but it never cools off enough to make it livable. Plus there's not a lot of free oxygen around there, so we're not going to be going there and breathing anytime soon. Now, when we go away from Venus and go towards Mars, Mars has held a fascination for people for a very long time. Even before we could get really good images of Mars, people wondered, are there people who live on Venus? Are there people who live on Mars? We always seem to have more of an idea of Martians than we had for the Venusians along the way. And if we sort of think about it, we've had different kinds of stories, we've had different kinds of science fiction that has talked about something called LGMs. And do you know what LGMs are? What that stands for? I'll give you a second. Think about, what color is Mars? In this, of course, it's black and white. But the color of Mars, as we can sort of see from what we're looking at behind there, it's sort of a reddish color, a rusty color, which makes it surprising that we would talk about LGMs. Did you get it yet? Little green men. That's what LGM stands for, little green men. Why would green men come from Mars? I know Marvin the Martian is a sort of greenish in part of his coloration. He's a weird character along the way, but we've had this fascination with Mars. We've been able to get some fairly good pictures of Mars for more than 100 years. If you have a good telescope at home, you might be able to just make out the polar ice caps. You might be able to make out some of these structures here. Of course, we have much better images from our major telescopes like the Hubble, as well as the probes that have gone to Mars. But one of the early stories of Martian exploration from our surface involves a guy named Percival Lowell. And notice Percival Lowell down here. He built what was for a time the best telescope in the world, in the best location in the world, out in the American Southwest. And he looked up at Mars and he saw this, or at least he claimed to have seen this. And part of this is a misinterpretation of what he was reading. Notice that as we're looking at Mars through the same telescope he looked at, or looked through, because it's still around. We can see this. This is, however, what Percival Lowell drew, and this has all sorts of canals. Now, why did he draw canals? Why did he think he saw canals? Well, if we think about the word canal, there was an Italian astronomer named Schiaparelli who wrote a book about Mars and claimed that he saw through his telescope canali. Notice the I that's there. Now, that should translate into, in English, the word channel, not canal. You think about canals, you've got the Panama Canal, you've got the Suez Canal. I've got me a mule and her name is Sal, 15 miles on the Erie Canal. They're all made by human beings. Channels, on the other hand, the English Channel, people swim the English Channel. Those are natural phenomena. If you look at the picture on the left here, we see some dark markings that could be major channels, although this is much larger than any channel you would see. Where did all of this stuff come from? Well, there's an intriguing idea that someone floated just a few years ago, that as Percival Lowell, we see him here looking through his major telescope down in Arizona, as he was looking through this, if you've ever tried to look through a telescope, you sort of look through the eyepiece and you have to sort of look around and try and find the image, because sometimes you're going to be looking at a mirror. Sometimes you're going to be looking at your own eye. And there's an idea that when he was looking through his telescope, he was actually seeing the back of his own eyeball superimposed on the image of Mars. Now, the back of your eyeball, your retina, is reddish in color. So is Mars. So he might not have known. And since this was the best telescope in the world at the time, especially for this kind of viewing, no one could tell him he wasn't seeing that. The possibility is he actually did see that and didn't know that it was actually an ophthalmologist who came up with the idea that he might have been looking at the back of his own eyeball. This is what we see when we look at it through the Hubble. No canali, no channels, no canals. Although we can give Schiaparelli and Percival Lowell a little bit of credit here, that this in fact looks like a canal. This might look like a canal from a very small image that was unclear. So this is a good image, but notice we're still not getting a lot of detail, and we're certainly not picking up any canals. We are picking up the ice caps, North Pole and South Pole. We're picking up these cloudy areas there. They're called hoods. They grow seasonally and shrink seasonally. We see there's a little bit of coloration over here. There are other cloud formations. Sometimes the whole planet gets clouded over, and sometimes it gets clouded over due to sandstorms rather than just the H2O and the carbon dioxide and other kinds of things that are in the atmosphere. We've had probes going to Mars for also about half a century. In the past 25 years, we've been sending things increasingly complex as rovers. Here's the Pathfinder, see it over here. It's about the size of a standard microwave oven. It landed in this, this is sort of like a lander that was surrounded by all sorts of airbags, sort of like the airbag technology we use in cars right now. And it would sort of land and bounce and bounce and bounce, and then everything deflates. It would set itself with its gyroscopes upright. It would charge itself on these solar panels. Notice it also has solar panels on the top. But Mars is twice as far away from the sun as we are, which means, if you remember way back when we were talking about light and other kinds of things, it means it gets only 1/4 of the sunlight in terms of power as we do here. So you have to have a lot more charging capability to run the same kind of stuff. So it didn't go very far. It was mostly a test to see whether this kind of technology would work on Mars, and it did. So we've gotten more and more advanced. And the Spirit and Opportunities were both much larger, say the size of a desk, a large desk. The Curiosity is maybe about the size of a small Jeep. The Curiosity, it actually has a nuclear battery, not just solar panels. So the solar panel ones landed near the equator, where it's going to get the most sunlight for the most amount of time. Curiosity can go higher and lower in latitude, so it can go around there. We can sort of see from this map, here's where Curiosity landed, and it's sort of taking off north from and south from there. Spirit and Opportunity also landed in the areas of the equator going to be right in the center here, and they never strayed too far from that. The Pathfinder also not too far from the equator, but in a softer area. Viking 1 and Viking 2, they both landed in the 1970s, and they were stationary, so they just sort of landed in one spot and stuck to their position. The Phoenix landing site up here helped us to understand the polar ice caps that are there. We've had others that are there as well. Someday we might take a trip over to Olympus Mons. That's sort of on the docket for one of the next sort of half dozen different trips of probes to Mars. Notice we also have other volcanoes that are here. We have much smoother areas up here, much more pockmarked areas down here. This is where the oceans were, up here at the top. So as something came in and hit the planet, it would hit the oceans and not leave craters. There was also a big inland sea here in the Hellas Basin along the way. And we can actually trace the river connections that connected that to the oceanic areas along the way. We've tried to land in some places that are sort of near coastlines so that we can get a sense of the rockier areas that were higher terrain and lower areas that may have been underwater. And in fact, both of the Vikings landed in what we considered to be water-based areas in the hopes that if there was any life that survived on Mars, it might have been where the water used to be on the surface. Lots of early craters have been erased, especially when there was water and when there was a thicker atmosphere. Now, if Venus over here has 100 times, 95 times the atmosphere of the Earth, then Mars over here only has 1/100th, 1%. So to get the atmosphere for Venus, you multiply Earth by 100. To get Mars, you divide by 100. But that means you don't have strong storms on Mars anymore. So the weathering takes a much longer time. But there is an atmosphere, unlike Mercury or the Moon. So there is an atmosphere that actually does change things along the way. The Victoria crater here, you can see that. All of this stuff that's in the middle there, those are sort of blown by the Martian winds. But notice as we have this sort of curvature and the wind blows over the top, it dips down a little bit and then curves back up. So you're only getting the ripple effect from the wind here in the middle. The wind misses all of this area. And the Opportunity probe actually went up to the Victoria crater and scooted around it for quite a while. It didn't go down because we were afraid if it went down, it might not be able to come back up again. We didn't know whether this terrain was too loose to keep it from tumbling down or too loose to let it drive back up again. But we did explore the Victoria crater quite extensively with the Opportunity rover. We've never had a sample return mission from Mars, but we do have a couple of rocks from Mars that have landed here on Earth. If you have a big impact, like the Victoria crater here, hitting it, there's less gravity on Mars. Remember, Mars is much smaller, much less gravity, which means if you have a really big impact like this, and this is as big as a city, then it can throw rocks up, and some of those rocks might be thrown up with enough force that they break free of the gravity of Mars, they float through space and then get caught in our gravity and land on our planet. And that's how we have discovered several Martian rocks here on Earth along the way. Here we can see the sort of the radar mapping. Even though we can see the surface of Mars, we also do the radar mapping to tell the depths, and we can tell where the the lowland areas where the oceanic areas used to be. We can see where there are some huge mountain ranges and some huge volcanoes, not just Olympus Mons, but several others along the way. And then we have this long strip here called the Valley of the Mariner spacecraft, Valles Marineris. And it may have been one of those canali, one of those channels that Percival Lowell and Schiaparelli were seeing. Here's Olympus Mons. This is about the size of the state of Missouri. And if you take this whole picture, here it's even a little bit larger. This whole picture would be about the size of Arizona. So you think about the size of a mountain on Earth, it would probably be about the size of this little thing. Mount Everest would probably be about the size of this little thing right down here in the corner of Mount Olympus. So this is a huge thing. It's 5 times taller than Mount Everest is. But if you think about the way things are structured, you can build higher and higher and higher if you have less gravity pulling down. So we have this. Now, if you ever saw the movie Total Recall, Arnold Schwarzenegger, the original movie Total Recall, Arnold Schwarzenegger finds a door in Olympus Mons and runs to the center and turns on the atmosphere, and the atmosphere comes back to Mars. That is wrong in so many ways. Movies interesting and really good in some ways. Scientifically, it sucks. But here because how can you like go to St. Louis and then run halfway across the state in a minute and a half when there's no air? It doesn't happen, even if you're Arnold. So not so good on the science. But the other problem with that is you don't want to release the atmosphere to a planet that doesn't have the gravity to hold on to it. The reason why Mars doesn't have an atmosphere, in part, is because of this. This is an extinct volcano, or at the very least, a dormant volcano. It's not operating anymore, which means anything that gets leached out of the atmosphere into the soil stays there. It doesn't come back into the atmosphere. Also, if it did, there's not enough gravity on the planet to hold on to it. It's going to leak away. That's why Mars has such a weaker atmosphere than what we have. Here's another view from sort of straight down. We can see some craters here. That's another thing that tells us that this volcano is extinct, because if we had lava still flowing, these would have been overflowed and it would have erased them. But this is a shield volcano, which means it just sort of bubbles up and bubbles up and bubbles up, and that's how it built up to the high structure that it has here. Now, here's the Valles Marineris, the Valley of the Mariner spacecraft. This leads up to, from this area to this area, up to the volcanoes, just off the picture here. This is not like the Grand Canyon, which had a river running through it. This was a lava tube. This was where the magma flowed and flowed up into the volcanoes. When the lava stopped flowing, when the magma shut off underneath, that's when it collapsed in on itself. It's 3,000 kilometers wide. Basically, that means it goes all the way from New York to Denver, maybe even a little bit further, depending on where you have the end here. It may all go all the way across the United States. And it says here 8 kilometers deep, which means it's 4 miles deep. In fact, there are some portions of it that are going to be even deeper than that along the way. So if you were to stand on this one side over here, you could not see all the way to the other side. It is that wide, it is that deep. And this is part of the tectonic structure of Mars as well. And here's a great picture of it. I really love this because you can see it takes up almost an entire side of the planet. It starts over here, flows over here, and we have our volcanoes here. And Olympus Mons is just off the side, just off the horizon of Mars over here. This is a great shot. Here we can see landslides. This is where the ocean was. This is where the higher land was. There was ocean over here. So this might be like the Florida of Mars, because you have the Gulf over here and the ocean over here. And we can sort of see where the two meet up, and we can see more landslides happening down here and some flows that go into the oceanic area. Where we've landed, we have a lot of areas, especially Pathfinder and both the Vikings were landed in areas that were probably underwater at one point. And these have lots of areas that look like they're the bottoms of dried up oceans. So it is rather interesting that we have a consistency in different parts of the planet. But here we have Utopia. You may have heard from Star Trek Utopia Planitia, where starships are made and other kinds of things. That's a real place. That's a real place on Mars. And it has frost. So we have frost that forms just like it forms here on Earth. Stuff freezes out of the atmosphere onto the ground and then evaporates later in the season. Here we can see the tracks of dust devils. Just like here on Earth, if you ever go to Walmart and see the little Wendy's bag going around in the little dust devil kind of miniature tornado, we have those on Mars. Those were first found by the Viking explorers. They were taking pictures. They didn't have video, but they were taking pictures, and we thought, what's that thing there? And I'm old enough to remember when we first saw those, and that's what they are. And then, of course, we have our sand dunes. See the ripple effect here. That's sometimes called cantaloupe terrain, because if you pick up a cantaloupe and you sort of feel its ridginess and its edginess, that's what's happening here along the way. Here we can see in the sort of the rocks even. These are long straight ridges that are being dug from the wind. Even though there's not much wind, it's my breath, if I sort of held something and went, I'm putting out more force than the typical windstorm is going to be putting out on Mars. But if I do that for 2 billion years, it's going to wear this away. It's going to wear me out too. But that's what's happening, because it does pick up grains of dust and grains of sand and will blast, sort of sandblast this, a very gentle kind of thing. But again, after billions of years, you get an effect. You get an effect that's happening here. Here we can see the North Pole. Just like here on Earth, the snow caps grow in the winter and they shrink in the summer. Mars is also tilted like we are, if you remember. Any planet that has a tilt has seasons. We're tilted at 23 degrees, 23.5 degrees as a planet. Mars is tilted just a little bit more than that. We actually wobble between 22 and 25 degrees. Mars actually goes 0 to 60. So it goes quite fast, or quite a bit farther. And it goes more on its wobble a little bit faster than we do as well. Mars does actually spin on its axis. It's just about half an hour longer per day on Mars than it is here on Earth. But it does have seasons just like we do. So we can watch the polar caps grow and shrink. Some of that frozen stuff is H2O. Some of that frozen stuff is dry ice, if you've ever played with that. And we do have different kinds of ices that are just below the surface. When the Phoenix landed, it actually dug into the soil. And notice here we have some frost that's forming that again begins to shift as it gets hit by the sunlight along the way. Here we have a gully that formed. Obviously, this looks like something liquid. It's like something liquid burst from below the surface and landed in a puddle before it froze or evaporated away. That's one of those two things will happen on Mars. There's not enough atmospheric pressure. It's not just the temperature, it's the atmospheric pressure. When there's only 1% of our atmosphere, there's not enough to keep water, H2O, liquid. Which means if it is liquid below the surface, because it doesn't need to have the atmospheric pressure, it's got other forces working on it there. When it bursts through, one of two things happen, quite frequently about the same time: freezing and evaporating at the same time. It's a fun thing. You can actually go on YouTube and watch that happen. Here we can sort of see dried up riverbed. Notice wind doesn't blow like this. Wind doesn't go like this. And it certainly doesn't go around the way. But we can see where the wind is having an effect. We can see our cantaloupe terrain here. This is the sand dune stuff. So it would not actually be affecting this. But notice also here on the sides, it almost looks like it's damp. It almost looks like it's actually bursting through with a little bit of water. Notice here, we have another thing that looks like a riverbed that created a little island as it was flowing around. And we have some other cracks and crevices, runoffs and outflow channels. But here, as I mentioned before, the gullies. Notice here we see a lot of them that could be gullies, could be outcroppings of moisture. Here it looks like also we've got like outcroppings of moisture. It looks like they are flowing water from just below the surface. They're also seasonal, they change. So that if it was something else, if it was just something that happened to the geology, it's less likely to be seasonal. Here we can also see some dark streaks that are forming. So we have stuff just below the surface, and we keep getting more and more and more details and more evidence of liquid collections, liquid lakes and ponds and streams just below the surface on Mars. And that's one of the things we hope to explore in the next 20 years. As we look at the different things on Mars in terms of terrain, we can see where we used to have some rivers that would connect the oceans to inland seas. And we can tell from different infrared and visual light region evidence of things that were happening in the past. We look at the Gale crater here, we look at these kinds of formations. This looks like the shoreline. This looks like the beach, and this looks like the rocks that were being hit up and down with the waves over and over and over again. There would have been wave action on Mars, not as high and low of tides that are happening here on Earth because there was no big moon to pull on it. But when we're looking at this, we can tell this is stuff that really suggests water. And then we have this. These are called blueberries. Now, they're not the kind of blueberries that you put in your yogurt. These are blueberries that are sort of metallic things that on Earth form underwater. Now, one of the places, notice this is Utah. If you go to Arizona, New Mexico, Utah, Nevada, guess what? You're walking on the bottom of an ocean. That used to be a huge inland sea, and I would even argue that it was an ocean. The Great Salt Lake in Utah is the leftover of that sea or ocean that dried up. That's why it's a salty lake. The Great Lakes, Lake Michigan, Lake Superior, Lake Huron, Lake Erie, Lake Ontario, are freshwater lakes. They're melted glaciers. This stuff here is not. This is oceanic water. This is the leftover of what happens when the ocean dries up. Guess what we found on Mars? Blueberries. This is what happens when the ocean dries up. So yet more evidence. And then we have these kinds of rock formations. I mean, this almost looks like someone was making a wall for the garden. So maybe those little green men are somewhere to be found somewhere. But notice we've got our little blueberries all over around here too. So two different kinds of things indicating water. Then we look for hydrogen just below the surface. Guess what? We've got a lot of it here in the polar regions, and we've got a lot of it here in the smoother regions where the oceans used to be on the surface. We might still have some subsurface lakes and maybe even seas, maybe even small oceans there. And then we have the face. Here's the face. This, of course, if you've ever watched Ancient Aliens or other kinds of things like that, they make a big deal about the face. This is probably not the Sphinx. This is probably not an alien structure. If you look at it in other light, like over here, it changes its aspect. This looks like a human face, but when you look at it over here, this actually reminds me a little bit more of a lion face. So I'm thinking Simba, who was sort of up in the clouds, kind of reigning over the group after a lion king dies. So this is sort of like the brow, and this is the snout and the mouth of the lion. It looks more like a lion in this image than this one here, which of course, depending upon where the sun is, the sun would be up in this direction because that's where all the shadows are hitting, in that direction there. Whereas when you have the sun over in this direction, it changes quite a bit when the way we're looking at things. So chances are this is not Marvin the Martian's construction along the way. Looks like a natural outcropping, and it changes its appearance depending upon how the light hits it. But it is intriguing nonetheless, and it's one of the more fun things to explore. So there we are for chapter 10. I will see you next time for chapter 11.